So in this video, we start generalized inverse of a matrix. So what is the concept of generalized inverse? Now, to understand the concept of generalized inverse, we have to understand what do you mean by a system of linear equation. So system of linear equation is like that: Ax equal to b, where say A is an n cross A matrix, and X is m cross 1 vector, and B is n cross 1 vector. So that means there is a n cross m matrix. So here n rows and m columns, and you have to multiply with this a m cross 1 vector. So it is m, it is 1, and that is equal to n cross 1. So better I put some, say m is large and n is a small thing, then this m equal to m, and then n is a small n cross 1. So this is the basic format of system linear equation. What we can write in the form: if matrix A is Aij, then we can write this matrix, and X is say x1, x2, xm, and B is say b1, b2, bm. We can write this system linear equation like a11 x1 plus a12 x2 dot 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 a1 m xm is equal to b1. Similar, there are other n equations. So here is n equations and m many variables. Now, how to multiply this matrix? Actually, we are multiplying this matrix with this row. Sorry. So this column with the first element, and the next column with the next element, and so on and so forth. Dot, dot, dot. So that is the basic idea. So system linear equation or matrix multiplication can be written in like that. So it's actually x1 a11 a21 dot 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 an1 plus x2 a12 a22 dot 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 an2, and the xm into a1m a2m dot 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 anm is equal to b1 b2 dot 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 bn. This is a system linear equation. You can write in this form. So system linear equation can be think in three different ways. It's just a school level idea is just there is some m equations, n equations, and of m unknown. So this m equation n unknown. But the better way to think is it's just a linear combination of some n dimensional vector. So n dimensional vector. There are m many vectors. There are m many vectors, column vectors, and these all are n dimensional vector. So it is a linear combination of n dimensional vector is another vector, but that vector is given to you. We have to find that as the coefficient. It's like a that equation, you can think like that. So it's like a vector equation. So you have to find the coefficient. Say a1, you can like this column vector like a1. This column vector is a2 dot 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 xm am is equal to b. Now this a1 is a column vector. Ai is a column vector. That ai, oh sorry, a1i, a2i dot 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 ani. So these are in Rn. If it is any other field, then it is that f to the power n. If you consider the real number, the coefficient as real number, just Rn, or you can take any other field also, any general field. Now this is here B is given to you, B is given to us, and A1, A2, Am is also given to us. So that matrix A can be written as like this, like a partition matrix, some m many column matrix, column vector side by side. So A can be think as a bunch of column vectors of m many column vectors, each are in dimension. So it is n cross m matrix. So we have to find the coefficient. We have to find the coefficient for which coefficient these are B. Now there is several issues, like if there may not be exist any such coefficient. There may not be exist any such coefficients such that their linear combination is B. It can be happens that say your A1, A2, Am are say coplanar. All the vectors in a plane, say 2-dimensional. Okay, n equal to say 3, say n equal to 3. So vectors are 3-dimensional, but they are there are 5 vectors in 3 dimension, and these are in a plane. Now if B is a vector, 3-dimensional vector, we are taking n equal to 3 and m equal to say 5, and B is a vector such that this is not in the plane, then you can't write that vector B vector in terms of a linear combination of that coplanar vectors. So there is a question of whether B vector is in the rows column space of the matrix or not. So we know that span of this all column vectors is called the column space. So span of this column vector is called the column space, and if B in the column space of the A, that is the span of this vector column vectors, then we can write B in terms of that A1, A2, Am vector column vectors. Then we can find x1, x2, xm. How to find x1, x2, xm? There is a different issue, but we know there exists some x1, x2, xm. There are several methods to find this, like Gauss Gauss elimination method, Seidel method. There are other several methods like that. There are substitution method also in school. We know how to solve the substitution method. But the most popular method is Gauss elimination method. Eliminate one by one variable. So that is a different issue, different problem, how to solve this x1, x2, xm. And another problem is it exist or not? So obviously it is if and only B is in the linear span of this A1, A2, M, then this solution exists. Number one. Okay. If it is outside that column space, then it is not. System linear equation is inconsistent. Next question is okay, this B is in the column space, so solution exists. Whether this solution is unique or infinite many solution. We know if there is a not unique, if there is a more than one solution, then must be infinite. That we know. If there is 2 solutions, there is a infinitely many solutions of the system of linear equation. Now, how do you know there is a one or more than one? More than one means infinite. So that is depends on the question whether the B can be written as uniquely in terms of A1, A2, Am or not. So whether B can be written, is there exist in such? Can we write, the first question is, can we write B in terms of A1, A2, Am? That's the question whether B is in the linear span of A1, A2, Am or not. The second question is, if it in the column space, if we can write whether it is unique representation or not. If it is a unique representation, then x1, x2, xm is unique, so there is only one solution. If it is not unique, then infinite solution. Now from the vector space theory, we know if A1, A2, Am are linearly independent, then that B can be written uniquely in terms of A1, A2, Am. That means the system linear equation has unique solution. And if A1, A2, Am are not independent, if they are dependent, then we can write B in terms of A1, A2, M in more than one way. That means it's infinitely many ways. So this is the question of system linear equation exists or not exist. If it exists, then it is a unique or infinite solution. That we should resolve, and the question is how to find this number. Now, if A is a square matrix, then A is a square matrix. So is a square matrix, and n is x is n cross 1, b is n cross 1. Then we know this solution may not exist. If it is exist, then the one way to find that rank of that inverse, if A inverse exists, we know if A inverse exists, then x equal to A inverse B. A inverse B. By the way, another way to visualize that system linear equation like that, so it is Ax equal to B. So we can think like A as a function, linear transformation. So A is a linear transformation from Rm, right? There are n many yes, n many. There are n many x1, x2, xn. Yes, n many. So it is Rm to Rn. There is a linear transformation from Rm to Rm, such that for all x belongs to that, or you can think as a linear transformation t of A, such that for any x belongs to Rm, I just take t of what the transform output of x is just Ax. You can think like that. Now so since it is a transformation, so it is like a machine, it's a function. So you have put x here, and if you know that t, what is t from x, you can easily find tx, that is b. But the question is, if you know the b, how do you find x? That is a question of solution of system linear equation. If you know the output, how do you know the input? Whether this input exists or not. This whole thing is concept of whether function is onto or injective. If it is onto, then this function has every b for every b the solution. If it's not onto, then some b has solution, some b has no solution. And if it is injective, then every b has a unique solution. And if it is not injective, then some b has may have unique, some b may not have unique. So this question is actually related on the surjective or bijective or injective of this linear transformation. This is one issue, and another issue is like it's in a vector space concept. Is whether this is in the column space or not. Now the question how to solve this. So if A inverse exists, the problem is easy, and we know in this case it is a unique solution. So unique solution. Now if A inverse not exist, then there are several issues not exist. Then we know it may be inconsistent or it may be consistent. If it is consistent, then infinitely many solution. We know that because if rank of A is equal to rank of AB is equal to n, then only it is a unique solution. If rank of A is equal to rank of AB but less than m, sorry, number of variable m, then is infinite solution. And if rank of A strictly less than rank of AB, then no solution. So if A inverse not exist, okay, A inverse not exist but solution exists, rank of A is equal to rank of AB, then question, how do you solve this? What is the solution on that? So one technique is you just apply any method like Gauss elimination method. The problem with the Gauss elimination method is this, like that. So if you have a matrix given to you, not maybe it may not be if not exists, or A is not square. If not square, is not square matrix, then no question of A inverse. If it is not square or A inverse not exist, if it is square, still it is A inverse may not exist. In that situation, if we have A and we have to find that x, we have to find this x. What is this x? That is the question. We know A and we know B matrix. The question is, what is x? What is it? That is the question. So may or may not exist. If it is exist, how do you find this x? Now they go, okay, if I say it is okay, it exists, then you just solve this. Now the problem is with the Gauss elimination method is, okay, I ask you, okay, that B, I have another B, say, not B, I have another B1. You have to change that B to B1, another column. Then what is the solution? Then actually you have to solve again. The whole thing you have to calculate again. For any solution technique, that's the problem. The A is same. Now, if B is changed, someone say, oh, that B is wrong B. I provide you the wrong B. This is the correct B. Then you have to do the whole method, whole this laborious process once more. But finding A inverse is better, because if you have this A inverse, say you have A, you find A inverse, and then once you get B, you find A inverse B. If someone say, okay, I change my B, that B is not correct, okay, you can give me another B, I will find A inverse B. So the whole process is not needed. The A inverse actually depends only on the A. Once A is given, before getting B, you can find A inverse, if A inverse exists. So that is two things. So it is an offline and online calculation. Say, I give in to you A, and I say I'll give you that B in 1 day, after 1 day or 1 hour. You just calculate A inverse in between that time, and once you get B, you just find A inverse. That is easy. Finding some matrix multiplication is just a 1 minute work, just a single minute. But other who want to apply the Gauss elimination method, they have to wait for B. They have to wait for B. And so once this B, you get B, then he or she can find that A inverse, that solution. So that is the inverse technique is better in that sense that you can calculate something beforehand, offline calculation, before getting B. Now, question: if A inverse not exist, or A is not a singular matrix, square matrix, then can we do something with A beforehand, before getting B? Can we find something from A before getting B, that once I get B, I can find the solution? And if I change that my B, if someone change my B, then that work, finding something from A, is not hampering. So I'll not go to the solution directly. We will not use the Gauss elimination method directly. We'll find something using A, because once you are in the, you just think in the Gauss elimination method, we are just taking some multiplications, or multiply by a non-zero scalar, then take a difference, such a thing in Gauss elimination method. Multiply 1 by 2, 2 by 3, then take the difference. And you can observe that once you do this operation, that the column B, the operation on the column B is itself going on that. So from B, no one can affect the A, and from A, no one can affect the B. Every column is actually a row operation, so every column is actually changing. So the column 1 cannot affect column 2, column 2 cannot affect 1 or 3. Similarly, the column of A cannot affect B once you have this Gauss elimination method, or this row elimination, row operation, in row operations on the matrix. And column of B cannot affect that column of A. So can we something do with A such that before getting B, we find something about A, and then after getting that B, we do this, and that we can do, and that extract we can find from A to solve this equation is called G inverse of A. So we can find something G inverse of A before B, and once I get B, using the G inverse of A, we can find the solution. That is the motivation for finding G inverse. Now the interesting thing is, this G inverse is always exist for every A, even for null matrix. The G inverse of null matrix exists. G inverse of every matrix exists, whether it is square or non-square, it is a square, it is a non-singular or singular, whatever. The G inverse always exists for every matrix, even for null matrix also. And obvious thing is this: if A inverse exists, then G inverse is equal to that A inverse. That should be natural. Now, on the other hand, the other side of the coin is this: that G inverse is not unique. If it is unique, it is only one case it is unique, if A inverse exists. In that case, it is unique. Otherwise, it's not unique. So that means finding unique solution is just depends on the A inverse exists or not. So So G inverse, what is G inverse? So I have the idea, more motivation for the G inverse, and how to find the G inverse? That's the question. So I said that thing. So the definition of the G inverse, but there is again there is a one question: how do you get written in this definition? We have this. Okay, we have this motivation. We know how what we have to find, but how we find this. But before going into motivation, just that technical thing, we just define G inverse like that. So G inverse, like G inverse of A is G. So if A is an M cross N matrix, then G inverse of A is a N cross M matrix. Just order is changing. It's called generalized inverse. G inverse also called generalized inverse. So if AGA is equal to A, AGA is equal to A. So this is a definition. Now there are two things. We have to show that for this AGA, we can find the solution. Number one, that we will show. Now the other question is, from that idea, that concept, to find something from extract something from A, how I reach in this such a amazing AGA? Is nothing coming from the sky. It's not that if someone tell me, okay, take AGA equal to, and you can find that. So how do you reach in this thing? But this is actually some motivational part, but this is not related to the solution theorems or in syllabus. But what is in, we have to prove that for if AGA equal to A, then G has some beautiful property. What is that beautiful property? So this is the theorem. So why we take such a G such that AGA is A? The theorem is this: let A and G of matrix of order M cross N and N cross M respectively, then the following two are equivalent. So two things are equivalent. One implies two. What is two things? G is G inverse, G is and G inverse. So sorry, and A G inverse, because G inverse we don't know whether it is unique or not. We later show that the G inverse is not unique. So G is a G inverse of A, and even only for any Y in column space of A, because you need that Y means that B. Okay, we just take P. You can okay take put Y. So for all any Y in column space of A, Y that B actually AX equal to Y. You need that Y in column space, otherwise no solution. Then for any Y that GY X equal to GY, remember we have A, and from A we can compute G, and we have Y, we don't have X. So that X is GY, like A inverse Y. G is a, if A inverse exists and G equal to A inverse, is a solution of AX equal to Y. So AX is the equation. So Y is known here. A is known. From A we find G. The G has the property AGA is equal to A, and that finding, after finding that G, once I get Y, we calculate that GY, and we claim that my GY is a solution of AX equal to Y. So we have to show both way. We have to show that if AGA equal to A, then X equal to GY is a solution of AX equal to Y, and the other hand, conversely, if X equal to Y belongs to column space of A and X equal to GY is a solution of this, then AGA equal to A. So how to prove this? The proof is very easy. You just first take that this is a G inverse. Assume that G inverse, so 1 implies 2. How do you show 1 implies 2? So take this is a G inverse. Now take any G, any Y in the column space of that. Now since it is a column space of A, we know that is a solution. We know. So there exists a Z such that Y equal to AZ. We know that there is a solution. But I don't know what J is. But we know that some J is there. But we don't know how to find Z. But we know that there is a Z because Y is in the column space of A. So Y can be written in terms of the columns of A. So there is a Z. How to find that? Actually, that is not needed. That J is not needed. I know there is some Z. Using that Z, we prove that GY is the solution. That Z may not be that X. That what I get. So I know somewhere is something is there, and from that is unknown to me, but I know there exists something. And using that unknown but exist, using that Z, I calculate my Y. How? So what is this? So A G Y. So now Ax equal to AGY, x equal to GY is what is this? So it is AGY, but Y is actually AZ. So it is AGAZ, but AGA is A. We assume that G inverse. So it is AZ and AZ equal to Y. So X equal to Y, prove it. Prove it X equal to Y. For if X equal to GY, then X equal to Y. We have this. So that means X is the solution of Y. That X may not be Z. Actually, X will not be Z. If you take any some Z, you can reach to the another X because there is infinite many solutions. Starting from Z, you can find. So G is, since if you change your G, you will find different X. On the other way, if assume that we have to prove two implies one, so assume that there is a solution like that, and we have to show that AGA equal to J. But since AGY is the solution of this, so AGY is equal to Y. AGY equal to Y. For any Y in, for all Y in that column space of A. It is the column space of A that AGY is Y. Now, what is A? Since AGY is Y, Y is in column space of A, whatever. We have A, G, A, Z equal to A, Z for all Z. Now, Y is of the form AZ, since Y is in the column space. So, since Y is in the column space of A, that means Y can be written as AZ. So, I don't know what is AZ, but AGA Z equal to AZ, because I assume that 2 is true. I don't know whether AGA equal to A. I have to prove that AGA equal to A. Now that's a problem. Is AGA Z equal to AZ, then is AGA equal to A? We can't say directly that if AZ equal to BZ, then A equal to B, we can't say. We can't say that. But in this situation, we can prove it. Why? Because this is not true for just a single Z, it is true for all Z. Since it is true for all Z, we can say that AGA equal to A. If AZ is equal to BZ for all Z, then we can say equal to B. What is the idea? Idea is this. So you take Z as a Z as a ith column of the identity matrix. So first take Z equal to, say, choose your Z equal to 1 0 0 0. Then we have this. So say take Z1 is this. Then Z2 is the 0 1 0 0 0, and so on. Now AGZ1 is AGZ1, then AGAZ2 is AZ2 dot dot dot, and then clubbing all this side by side, you will actually find AGA, and this by the partition thing, Z1 Z2, that partition column, these are column vectors. What in N should be N? What is the order of A? Order of A is M cross N, so it should be N. It should be N. That is just A, Z1, Z2, Z. But this Z1, Z2, Z3 is the identity matrix, because the Zi is the ith column of the identity matrix. So it is identity matrix. So A into identity, we have the result AGA is equal to A. So that is a tricky thing. If it is true for some Z's, it may not true AZ equal to BZ. But if it is true for all Z, then it is true that A is equal to B. So this is the proof, beautiful proof, and this actually says that the G inverse, I have this G inverse and I have this for G, that G inverse have the desired property, and I need that G. But how we reach at this G, that is a different issue. I'll not talk on in this video. Next thing is, how do you find that G? That is the question. How do you find such a G so that AGA equal to G? And whether this G's exist, we don't know. Still, we don't know whether G's exist or if it exists, is unique or not. But later we say that G's exist for every matrix and it is not unique. Now, how do you find that G? So, to finding G, we need some rank factorization theorem. So, we know if A is a matrix of n cross m or m cross n here, yes, m cross n here. So, we have a rank factorization of that. BC is a rank factorization. It's a rank factorization of G, of A. Now, you know what is rank factorization. Rank factorization is like that. If it is a m cross n, then it is a B is m cross r and C is r cross n, where r is the rank of A. There is some matrix A. From A you can find BC using rank factorization, rank of A. And that B has full column rank, yes, full, C has full row rank. And rank of R is also rank of B as well as is the rank of C. We have this. We know from the previous lecture on linear algebra that this B and C exist for every A. There is a rank factorization, even if A is null matrix. Now, since B is a full column rank, it is not may not be square matrix, but the left inverse of B is exist. So there is a left inverse of B exists. Left inverse of B exists. What is the meaning of left inverse of B? You just multiply by the left, it will give your IR. You can't be multiplied by right from the right side. Then it is, you can multiply, but it is not then IM. And C has a right inverse. What is that? Right inverse is this. We know this. Now G is my so from B we can find that left inverse and right inverse. I have that my G. That my G is C R left inverse, right inverse of C multiplied by the left inverse of B, and this is my G inverse. But we have to prove that. Okay, we'll prove. AGA is equal to, we know what is A is BC, and what is G? Right inverse, sorry, right inverse of C and left inverse of B, then BC. The associative property, it is just C, C this, B left inverse, B C, and this is identity R, IR this, so it is BC, and BC is again A. So we prove it that this is AGA equal to A. There is one method to find G. There are several other methods. This is a theoretical method, but there is some other computational method. And there is a question of issues that in which method we have a less number of calculations. But this is not in our syllabus. Not in it is actually the algorithmic part. So some efficient algorithm to find a G inverse. That is a different issue. That is actually the study in computer science. What algorithm actually is the best algorithm? What is an efficient algorithm, and how much time to take to there's a the 2-3 hour algorithm, what is the best, which take the less time, which is the less memory. That is a question of computer science. We are not going into details in that, but this is one theoretical method, and this by this method you can find G. But next question is how time it will required, how many multiplication is required, how many addition is required, how many memory is required, but that is not our syllabus. Then another alternative method is method 2. Method 2 is to find G inverse is this. We know since A is a rank R, then we can write A like that. So we have some PQ non-singular matrix. So some PQ non-singular such that this happen. PQ non-singular, this happen. Now it can be verified that we can verify, it is easy to check that IR U V W at any matrix of Q, you have to choose the U V R W in the proper dimension. This is actually G inverse of this. This is a G inverse of that IR00. You can just easily check. You can just multiply IR00 with that. So this is your G, and this thing your G. The whole thing is your G, and this is A. So AG, you have to prove that. Just you have to prove IUVWQ, then IR00, then again IRVWQ, IRUVWQ, that equal to actually IR00. So you have to prove that AG equal to A. Oh, sorry, no, AG equal to A. So IR00, then IRUVWQ, then again IR00 is equal to IR00. You can easily show that. So just take as just as you say R matrix, and this take as I say J matrix. You just homework to show that JRJ is equal to J. So then we can claim that is a G inverse. That is easy to check. And then my G inverse of A is my G inverse A inverse G. What is the A? G inverse of A is Q inverse, then I R that U that V, the same W, and P inverse. Remember that Q and P are non-singular, so P inverse and Q inverse exist. And you can easily again check it that G is the G inverse of A. Check it. Check. It is A G inverse. Inverse of A. Now this method is slightly better in that sense. We already have the structure how that G inverse look like, and if you change your that UVW, you can take anything. And UVW is actually proper dimension. You take the proper square or rectangular thing, but you can choose your UVW as you. That means your G choice of G is not unique, basically. So even if any matrix is not square, the non-singular matrix has infinitely many G inverse. So it shows that actually from the color, when it's corollary, if A is not square, then there exist infinitely many such G inverse. G inverse of A. So you just choose your UV as your choice. And the third method is this to calculate G inverse. Is this method 3 is this that since A has a rank R, we choose suitable R cross R non-singular matrix A like A11, A12, A21, A22 is a choose any R cross R non-singular matrix submatrix. A1 is a R cross R non-singular. We can choose that. That is a trivial from our vector space, that non-singular. So if A has rank R, we have some independent R rows and independent R columns. You just choose that submatrix. Proper that independent rows, R rows, and independent R columns. With that, take that R cross R submatrix, and that will be the non-singular. And since A has rank R, there is a matrix X such that A12 equal to A11X and A22 equal to A21X. That we know from the vectors space linear from the previous linear algebra class, and it can be verified. You can easily check that your G is nothing but A1100. So what is the basic difference between this? Basic difference between this, you just find your UV, choose your AV. So no need of finding UVW here, but you have to calculate that PQ. Here problem is you have to calculate first A11, A12, and once you get A11, no need of getting actually A12. This to show that this is G inverse, you need that A13. to prove something. But finding that G, you no need of that A12, A22 or A21 matrix. You only need that A11 matrix. From A11 inverse, you just find G. But to prove that G is a G inverse, that needs something. So you have to say that this A12, A21, A22 exists. You no need of finding that to find G. So theoretical thing and this computational part is different. Actually, these aspects are different. The different aspects. So this you can check that this is a G inverse of A. So we use the notation for G inverse. Notation for G inverse is just G. The notation for that G inverse, like G is G inverse of A. We notation is A minus power. In power is minus, not minus only, just minus. This is the notation for G inverse. And obvious thing is, if A is non-singular, and obvious thing is, if A inverse exists, then this A inverse unique, only one inverse, and that the generalized inverse is same as our known inverse thing. So up to this part, up to this, in this video, next we'll show the other ideas of G inverse. What is the rank of that? What is the rank of this G inverse? And then why this is infinitely many so thing, and can you impose some extra condition on G inverse as that? So that can be unique. There is some 3 conditions on G inverse. There is one is called least squared G inverse. The extra condition on that G inverse. So it's just drops some G inverse which is not least squared, but still least squared G inverse is again infinitely many least squared G inverse. They may have infinitely many least square G inverse. Then there is one is called minimum norm G inverse. One is called minimum norm G inverse, and one is called symmetric G inverse. Sorry, reflexive G inverse. There are 3 types of G inverse, and this every type may have infinitely many choice. But that intersection, if once the G inverse has all these 3 properties, it is minimum norm, reflexive, and least square, then there is a beautiful theorem. We'll show that theorem, and we'll terminate about this course. Prove that thing, that there is one and only one G inverse for every matrix. Remember, for every matrix, not only for square or non-singular. It's for every matrix. For every matrix, there is a one and only one matrix G inverse. Obviously, if A inverse exists, that G inverse is A inverse, which has this all 3 properties. It is a G inverse, number 1, and the extra 3 properties is it is minimum norm. We'll see in the next video. Then it is the least square, and there is also reflexive. And if these 3 conditions hold for a G inverse, that means actually 4 conditions: the G inverse condition and the other 3 conditions. Then it is called Moore-Penrose inverse. So Moore-Penrose inverse is such a G inverse which have some nice property using imposing some extra condition, and that is unique for every matrix. So that means we can find the Moore-Penrose G inverse, and that's enough. No need of finding the other G inverse. You just find the Moore-Penrose inverse, and using that you can easily find the solution, at least one solution of the system equation. That's why this Moore-Penrose G inverse is so important. And Moore-Penrose G inverse or minimum norm G inverse have some nice property. Least square G inverse have some other nice property. Reflexive G inverse also have some nice property. Obviously, the Moore-Penrose inverse has all these nice properties of all 3 things. So we'll later in the next video we'll see that.